So we're now going to spend a bit of time looking at integration. The first part is both an extension 1 topic and an extension 2 topic, and that is integration by substitution. And the main difference is in an extension 1 exam, they'll usually give you the substitution to use, and they'll say, actually do it via this substitution, which unfortunately means you have no choice. You have to use the substitution they give you. Whereas in extension 2, then you can use what you wish. Now, the basic idea of integration by substitution is to turn it into a standard integral, something we know how to do. And so our standard integrals, the ones they give you in exams, so we start off with the simple one for a polynomial, which simply says, add 1 to the power over the power. All this on the right-hand side is just technically, because obviously n can't equal -1, or you'd have 0 on the bottom of the fraction. X can't equal 0, because otherwise you'd just be integrating 0. And if n is less than 0, x can't equal 0 if n is less than 0, because you'd have 0 on the bottom of the fraction. Don't need to worry about that. All we're really interested in is to see how it integrates. 1 over x dx is log x, technically when x is greater than 0, because really the integral should be log of absolute value of x, and then you can substitute, obviously, negative numbers in. Our exponential, they just do it for linear functions, so 1 over e to the ax. And then our trig functions, so cos goes to sine goes to minus cos, sec squared goes to tan. Then this is the one we used in conics, you may remember. Although we used it the other way round. We differentiate sec, we get sec tan. The ones we just recently looked at, the inverse trig ones, so 1 over a squared plus x squared, and the square root of a squared minus x squared, they quote inverse sine, but it could also be minus inverse cos. Then we have these other ones, which we'll see in extension 2, square root of x squared minus a squared, and the square root of x squared plus a squared. But as I say, we'll get to see what they're for later on. Then there are what I call non-standard integrals. They don't give you these, but it is very handy to know them to save yourself some time, because you'll be surprised how often they come up. So not listed, but will save us some time. Du over the square root of u. So if you want to integrate 1 over the square root of u, the answer is 2 root u. So 1 over root u, integrate it, you get 2 root u. That just saves a little bit of time. It's, turning into u to the power of negative a half, then add 1 to the power over the power. I mean, you'd end up getting 2 root u, obviously, if you did it that way. But you'll be surprised how often that little integral comes up. Similarly, du on u squared. So if you just have 1 over u squared minus 1 on u. Integral of log x, it turns out to be x log x minus x. And we will end up proving that when we look at something later on. And the integral of tan x, that's the one that's missing from our trig integrals, turns out to be the log of sec x. Remember, because we could rewrite tan as sine on cos, we end up with the log function. So log of sec. And the other idea I mentioned when we were doing trig is if you want to find the integral of a complementary trig ratio, then the answer will be minus the complement of the answer. So what do I mean by that? If I want to integrate cotan x, well, I've just said the integral of tan x is log sec. So cotan is the complement of tan, so the answer should be minus the log of cosec. So minus, and the sec changes to its complementary ratio. Yeah. All right. Minus log of cosec, you might prefer to write it as the log of sine, because you could bring the negative 1 in, and reciprocal of cosec is sine. Okay, let's have a look at some. So x times the square root of x squared plus 4. Now it is in the form, you'll notice, derivative times function, although it's not quite the derivative. And that's probably how I would do it in reality. But if they ask me to do it via a substitution, now when we are substituting, we're going to substitute u equals some function. Now you substitute the function that's causing the problem. The problem here is the square root of x squared plus 4. So I'm going to make u equal x squared plus 4, my new function. Now, there's x squared plus 4. That's what was causing my problem. That will become u. Now, I can't leave the x and the dx there. I've got to change those as well. Well, if I differentiate u, I'll get 2x with respect to x. We just split the du dx up. It's like if you multiply both sides by dx is the way you could think of it, I suppose. But so du is equal to 2x dx. So now I can see I've got, well, x dx will be a half of du. And I can substitute that in. I no longer have any x's in there. So I've got a new integral. It'll become a half the integral of u to the power of a half. That's the square root of u. We'll add 1 to the power over the power. So we get 3 on 2 and 2/3 times. But of course, that's in terms of u. Our actual question was x, so now I've got to substitute back in. So I sub back in x squared plus 4 everywhere I see u. That's probably how a mere mortal would leave it, but us super mathematicians, there we go. A third x squared plus 4 times the square root of x squared plus 4. Okay, I say, or. Okay, an alternative substitution for this one would be using trig. So if you see a root of a sum or a difference of squares, then you can create a trig identity which may well simplify the problem. So for this one, x squared plus 4, if I let x equal 2 tan theta, now what this is going to do is create the trig identity, tan squared plus 1, which I can change into sec squared, under the root sign. So dx is 2 tan theta, dx will then be 2 sec squared theta to theta, and now we can substitute in. So the x becomes 2 tan theta, the square root becomes square root of 4 tan squared plus 4, and then the dx becomes 2 sec squared. Now, the square root of 4 tan squared plus 4 is 4 sec squared. The square root of 4 sec squared is 2 sec. So all up then we've got 2 times 2 times 2, which is 8. Tan times sec squared, which is tan theta sec cubed. Now to integrate this, I rewrite it in terms of sine and cos. So tan is sine on cos. Sec cubed is 1 on cos cubed. So I end up with sine theta to theta on cos to the power of 4. I now need to do another substitution. If I let u equal cos theta, then du will be minus sine theta to theta. And now I can substitute in for that, and I get minus 8 times du on u to the power of 4. Of course, if you did notice, you had the situation of derivative times function to the power of n. You could have just added 1 to the power over the power with the cos. But we'll do the same thing here. U to the power of 4 in the bottom of the fraction is, of course, u to the negative 4. Add 1 to the power negative 3 over negative 3, and we end up with 8/3 sec cubed theta. But this is in terms of theta. We want it back in terms of x. So if I draw up a triangle, now we know that tan theta is x on 2. Bit of Pythagoras. We get square root of x squared plus 4. I can now substitute back in for sec. Sec is hypotenuse over adjacent. So we end up with sec cubed, so the square root of x squared plus 4 cubed over 2 cubed, which is 8, cancels with the 8 on the top of the fraction, and we get a third root x squared plus 4 cubed, which is, of course, the same. Now, I'm not suggesting you use this substitution. I'm just saying, here's another way we could have done it. Okay? Yeah. Keep an eye out, because in reality, if they did say don't use substitution, then of course we simply had derivative times function x to some power. So you see derivative times function x, you could just do a very simple way of doing it. All right, let's have a look at the next one. X plus 1 on 4x squared plus 8x minus 7. It's the bottom of the fraction that's creating my problem here, so I'd do substitution. 4x squared plus 8x plus 7. The derivative becomes 8x plus 8, and it works out quite nicely then. I just simply got an 8th du on root u. Sorry, on u. I keep saying root u. Just on u. So it's a log function. Substitute the u back in. There we go. That one's nice and simple. dx on x log x cubed. In this case, it's the log x which is causing me the problem, because it's the bit that's cubed. So u is equal to log x. Du would be dx on x. So this one tidies up to be du on u cubed, or u to the negative 3. Add 1 to the power over the power. Sub u back in, and I get 1 on 2 log x all squared. X on the square root of 1 minus x. In this one, I'm going to use the substitution x is equal to 1 minus u squared, instead of going u equals. Okay. So x is equal to 1 minus u squared. Again, it will get rid of the square root sign for me, because in effect what I'm saying is u will be not just the bit in the square root sign, but the whole square root itself. Okay. But because I've made x the subject, I can substitute straight into the x on the top. I can substitute in for the square root of 1 minus x. And I can substrate in for dx as well, because if I differentiate x with respect to u, I just get minus 2u du. So if you substitute u equals function x in, instead of x equals function u, what it's going to do is avoid any domain problems, because obviously we have restrictions on the domain here. And when you substitute in a particular function, you can end up with domain problems. Not an issue here, because it's not a definite integral anyway, but we just have to watch out for things like that. So I end up with 1 minus u squared on u times minus 2u du. Tidying all that up, take the 2 out, I've got u squared minus 1. So add 1 to the power over the power, subbing the u back in, which is the square root of 1 minus x, and there's my answer. Because I just had to. I couldn't leave it as the square root of 1 minus x all cubed. I just had to. 1 minus x times the square root of 1 minus x. All right, here's a trig one. The logical substitution here, of course, is the sine, because cosine is the derivative of sine. So if I do u equals sine, du equals cos x, but these limits refer to x, not u, so I'm going to have to change those as well. But I've got a formula there that will allow me to do that. U is equal to sine x. So when x is pi on 3, u is sine pi on 3. And when u is pi on 2, u is sine pi on 2. So my integral becomes the integral from root 3 on 2 to 1 of just u to the power of 5. Add 1 to the power over the power. But now I don't have to substitute back in, because it's a definite integral. I'll just sub these numbers in and get my answer of 37 on 384. Okay, x dx on the square root of 25 minus x squared. Okay, I'm going to make 25 minus x squared my new function over there. So du becomes minus 2x dx, which is nice because on the top I've got x dx. I'm going to have to change my limits. So when x equals 3, u is 16, x equals 4, u is 9. It becomes minus a half du on root u. Du on root u is 2 root u. Watch, this is how we get there. U to the minus a half, add 1 to the power over the power, you get your root u, or u to the half. So root 16 minus root 9, which is just 1. Here's an interesting one. Square root of 25 minus x squared. Now, you might think I'm going to use a substitution 25 minus x squared. Not going to work, because remember, if I said u equals 25 minus x squared, then du would be minus 2x dx, and I've got no x dx there to substitute into. this is one where it's going to be easier to use trig. So if I try and create a trig identity under that square root sign, so 25 minus x squared, well, 5 sine u would work. 5 cos u would have worked as well, but I've just picked sine u. So u, the actual substitution I'm really doing, is u is the inverse sine of x on 5. Okay. Dx will be 5 cos u du. The limits have now changed. So when x is 0, u will be the inverse sine of 0, which is 0. And when x is 5, inverse sine of 1, pi on 2. So the square root of 25 minus x squared becomes 25 minus 25 sine squared. The dx becomes 5 cos u du. Now 25 minus 25 sine squared would be 25 cos squared. Square root of 25 cos squared, 5 cos. 5 cos times 5 cos, we end up with 25 cos squared. Now, integrate cos squared. That's where we need one of our trig identities. Cos squared is, of course, the same as. Very good. Half 1 plus cos 2u. We can now integrate. 1 goes to u. Cos 2u goes to half sine 2u. Subbing in, and we finally come up with our answer. Now, if they had said, just solve this problem and had not mentioned integration by substitution, this would be a silly way of doing it. Watch this. Square root of 25 minus x squared dx. Oh, hang on a sec, I know what that is. That's a semicircle. I'm integrating from 0 to 5. Oh, that's a quarter of a circle. I just want that little bit in there. So it'll be a quarter of pi r squared, 25 pi and 4. Okay? If you recognize the shape, just use the formulas we already know rather than integration. Going to save you, as you can see, a lot of time. So don't forget about algebraic manipulation. Okay? So we've got x cubed, the square root of 4 minus x squared. We can manipulate this into something we can handle. Watch this. X cubed, I'm going to change into this rather strange thing. Minus x times 4 minus x squared plus 4x. All right? Right? In other words, what I'm saying is x cubed is minus x times 4 minus x squared plus 4x. How do you work it out? That does turn out to be x cubed. So I've just manipulated x cubed. You're probably looking at it thinking, why on earth would I do something like that? Because now, when I expand out, I have minus x times 4 minus x squared to the power of 3 on 2, which I can do with a substitution 4 minus x squared. I've got the x out front, which I'll need for my du. And this one will become 4x times 4 minus x squared. So I can now do it via a simple substitution. Okay. Now, I'm looking at it rather than doing a substitution of thinking, okay, it's in the form derivative times function to some power here. Okay. Don't forget that simple idea. If they're not asking me to substitute in, I'm not going to waste time. Right? Derivative of x squared, 2x. I've got some form of the derivative out the front. Okay. So that's why I've got a half, because the derivative should have been minus 2x. So a half times, add 1 to the power over the power. Over here, the derivative should have been minus 2x. It's 4x. So it's minus 2 times add 1 to the power over the power. And so that's my answer, because I just can't leave those things with fractional powers. I know, I'm obsessive about it, but what can I say? So some of these interesting integrals, you can manipulate things to make them a little bit easier for you. All right. Are we going to have some fun or what? So the first ones are from our 3-unit textbook. So they'll basically have the substitution given to you. And then these ones from our Patel, our Pretend Cambridge. So A mixture of which?